A very simple overview of MOSFET structure and how it operates. Basically, how a transistor operates as a switch. So, going to a mechanical switch or a relay, let's imagine we have two metal pieces. Let's call them source and drain. And then we have a little filament that's suspended on a spring. And then we have a magnetic core, and there is a coil that's or solenoid that's basically wrapped around it. Let's imagine that the source and this terminal of the coil basically are connected together. They are connected to ground, and then we have a voltage difference that's applied between the drain and source. So nominally, if we apply 0 volts at the gate terminal, this terminal, there is no magnetic field, and essentially the filament is just further away from the source or drain, so there is an open circuit, or the relay behaves as an open circuit. And once we apply a gate to source voltage, once we apply a voltage difference between the gate and source, essentially a magnetic field will be produced in the solenoid, and this magnetic field will gradually pull this filament towards the drain and source until it shorts the drain to the source, and the relay basically behaves as a short circuit. The voltage value at which the relay, the filament touches the source and drain is called the threshold voltage. So when the gate to source voltage is larger than the threshold voltage, we make sure that the filament is essentially shorting the source and drain. Otherwise, the filament will be farther away from the drain and source, and essentially the switch will be off. So when the gate to source voltage is larger than the threshold, the switch is on. When it's less than the threshold voltage, the switch is off, or the magnetic field is not strong enough to pull the filament towards the source and drain to short them together. Now let's look at the structure of the transistor or the MOSFET specifically. We have a piece of silicon, and this piece of silicon is doped with p-type material, which is a material that's rich in positive charge, or essentially holes. So we have the p substrate, and then in this p substrate we heavily dope two regions with n-type material, which is a material that's rich in electrons. And then let's first explore this structure. Let's say the right terminal, we have a metal contact here. This is the drain essentially, and it's called the left one as the source. And let's imagine, by the way, the substrate also has a contact, and usually it's called the substrate or the body terminal. Generally, when you have a p material that's touching in an n-type material, what's happened essentially, you form a diode, p-n junction or diode, okay, for simplicity. Again, this is a very simple overview of how a MOSFET or a transistor operates as a switch. And so here we have two back-to-back diodes, because this terminal is the p substrate, and then we have the n region. This is the negative terminal of the diode or the cathode, and then we have another diode here. So two back-to-back diodes. And typically the source and the body, or the body terminal or substrate terminal, is connected to the source terminal, and say we connect them to the ground. And then let's apply a voltage difference between the drain and source. Let's call it VDS. say it's like half a volt, 1 volt, something like that. So in this position, since this terminal, which is the P terminal, is essentially equal to the source, so this diode is shorted, or essentially, yeah, you can remove it. Now, when we apply voltage difference between the drain and source terminal, as you can see, you have a diode, reverse bias diode. Essentially, if we look at the equivalent circuit, this is the VDS, this is the drain and source. At the drain, we have the cathode terminal of the diode, and at the drain and at the anode or the anode terminal of that diode or PN junction is connected to the ground. So as you can see, that's a reverse bias diode. So essentially, current cannot move from drain and source, and basically the transistor is in the off state. Now, in order to turn on this transistor, we'll need to essentially have a gate just like the magnetic core and the solenoid. However, how we establish the gate in a transistor, a semiconductor device, we put an insulator, a silicon dioxide, which is an electrical insulator, and then we have the gate, which is just a metal electrode. And then when we apply a voltage difference between the gate and source, what will happen? So let's sketch again. Usually, let's say call this is the source, this is the drain. We have a voltage difference here between the drain and source. The body is typically connected to the lower potential or the source terminal. Here we have the drain source voltage. Here we have applied a voltage difference between the gate and source. So this voltage difference, essentially what will happen is it's going to establish an electric field between this metal, the gate, and the channel that's underneath, or the semiconductor underneath. And essentially what will happen is electrons will start to be pulled from the source, most of them from the source and some from the drain, gradually, until enough number of electrons is accumulated underneath the gate. And this enough number of, or when the number of electrons that keep accumulating underneath the gate reaches certain critical number, essentially it becomes the channel becomes, or this region which we call the channel, the region that's being filled with electrons, the channel reaches essentially the point where it starts to conduct or cause a short circuit between the source and drain. And the voltage value of the gate to source that causes the enough number of electrons in that channel so that the channel connects the source to the drain or behaves as a short circuit between the source and the drain is called the threshold voltage. So again, we can say that when the gate to source voltage is larger than the threshold voltage, the switch is on, and essentially it establishes, as a transistor establishes a conducting channel between the source and drain. When the gate to source voltage is less than the threshold voltage, essentially there isn't enough electrons to establish a conducting channel, so essentially the transistor is in the off state. Just like as I mentioned about the solenoid that's wrapped around a magnetic core, the magnetic field, the threshold voltage essentially represents the voltage value that will cause enough magnetic field to pull the filaments towards the source and drain and cause shorting between the source and drain against the force or the pulling of the spring. Now again, I mentioned that when we have enough voltage difference between the gate and source, we pull enough electrons underneath the gate, underneath the gate, that establishes a conducting channel between the drain and source. Or of course, the body and source terminal are typically shorted together or connected together. This region that contains the electrons, the conducting electrons, is called the channel. And in this case, since we are relying on electrons for the conduction, for causing the conduction of the channel, is called an N-type channel. or N-type MOSFET, and essentially we can just call it NMOS instead of N-channel MOSFET. We can just call it NMOS for short. And of course, this is called the substrate. Now let's take a look at the current in the transistor as we change the voltage difference between the drain and source. So this is the gate terminal, this is the source terminal, this is the drain terminal. We have a voltage difference between the drain and source, voltage difference between a gate source, and we have drain to source current IDS. This is VDS, and this is basically IDS. And what happened essentially, as we increase the drain to source voltage, we said that the transistor, once it's, of course here we are assuming the gate to source voltage, this gate to source voltage is larger than the threshold voltage. So essentially the transistor is on and there is a conducting channel that connects the drain to the source. But we mentioned that this conducting channel has a finite equivalent on resistance, we call it R on. So essentially, when the transistor is on, it behaves as as a resistor. And if we have a resistor, and this resistor we apply a voltage difference across its terminals, say VDS, and we increase this voltage VDS, what will happen? The current in this resistor will increase linearly from Ohm's law. And the slope of this line is equal to 1 over the equivalent on resistance of the transistor or the resistor in general. Okay. Now, what happens as we increase the drain to source voltage further? Is it going to increase to infinity? No. What will happen? The current is in the transistor saturates. Okay. The current saturates. I saturation. So it has a peak value at a specific gate to source voltage. And the point that it saturates at, or you can consider, if we make this curve more steep, so this point, this VDS value is called VDS sat, is equal to what? Is equal to the voltage difference between the gate source minus the threshold voltage. So once the drain to source voltage exceeds VGS minus VT, the transistor current saturates, as shown here. It reaches a constant value as shown here. It doesn't increase linearly anymore. So this region we call the saturation region, and as a condition for it, or this region is defined by drain to source voltage that's larger than the applied gate to source voltage minus the threshold voltage. On the other hand, this range is called what? The triode region. The triode region. And to be more specific, the region where the transistor behaves exactly as a resistor and essentially its current increases linearly with the voltage that's applied. So in this region, as you can see, the current is a straight line. Here it starts to curve and saturate, right? So in this region, where the current is linearly proportional to the drain to source voltage, is called deep triode region. Deep triode. Now, let's see what will happen when we increase the gate to source voltage. So all this plot was at a specific gate to source voltage value. Now, let's use two values for the gate to source voltage for the same transistor and vary VDS and see how the current in the transistor will look like. So one time we'll apply VGS1 and then we'll apply VGS2. In each case, VGS1 or VGS2, we're going to sweep VDS from 0 to a large value. So this is VDS and this is the current IDS. So as I mentioned, under VGS1, for example, as we increase the drain to source voltage from 0, the transistor behaves as a resistor and the current increases linearly, but then it starts to curve out and essentially saturates. The current in the transistor saturates, and it will saturate at a value equal to VGS1 minus VT. Now, when we apply VGS2, the same thing will happen, and assume VGS2 is larger than VGS1. So if it's larger, what we'll find is what will happen, the current will increase for the same drain to source voltage. So what I mean is, in the triode region, we'll find that essentially the current will be higher for the same VDS value. Say this is VDSA. So for the same VDSA, VGS1 causes a current here in the transistor, while VGS2, since it's larger, it causes higher current for the same VDSA value. So essentially the current increases linearly under VGS2 and then until it saturates. And we said that the point at which it saturates is equal to VGS2 minus VT. So here there are 3 observations. The first one, the slope of the line in the triode region increased when we increased VGS. And we said that the slope of this line in the deep triode region is equal to 1 over R on the equivalent on resistance. So when we have VGS1, we have 1 over R on 1. When we have VGS2, we have 1 over R on 2. So obviously the value of R on 2 is smaller than R on 1, and that's for VGS2 that's larger than VGS1. So basically what I'm saying here is the equivalent on resistance of the transistor is inversely proportional to the gate to source voltage, VGS. The higher gate to source voltage, the more conducting channel we have, and so the smaller the equivalent on resistance of the conducting channel, and that's why for the same drain to source voltage, essentially we get higher current from the transistor or between the drain and source. Okay, so the first observation, the slope of the line increases, and this means basically the equivalent on resistance of the transistor decreases, and in general this means that the equivalent on resistance of the transistor is inversely proportional to the gate to source voltage VGS. Okay, and by the way, as we're going to see, it will be inversely proportional to the gate to source voltage minus VT, the threshold voltage. And why that is the case? VT represents the gate to source voltage that causes enough number of electrons in the channel to cause conduction between the drain and source. And so any voltage higher than this threshold voltage will cause more electrons into the channel. In the conducting channel, it will increase the number of electrons in the conducting channel, so it will improve its conductivity, or essentially is going to reduce its equivalent on resistance. And that's why the equivalent on resistance of the transistor is inversely proportional to VGS minus VT. And since the excess voltage that's higher than the threshold voltage is basically accumulating more electrons than what's needed to just cause enough conduction between the drain and source, the value of VGS minus VT, we call it V overdrive, VOV, V overdrive, because it's higher or in excess than the threshold voltage. V overdrive, also we call it the effective voltage, the effective gate to source voltage. So V overdrive or VOV. Now, so that's the first observation. The second observation, as you can see, is the saturation current for under VGS1, ISAT1, is going to be smaller than ISAT2. So what we can conclude is the saturation current is proportional to to VGS, and later on we'll see that it's proportional to VGS minus VT, the overdrive voltage, because it represents the voltage in excess to the threshold voltage that increases the number of electrons and what's needed. That's the second observation. What is the third observation? Well, the third observation, VGS1 minus VT, that represents the drain to source voltage that causes saturation, VDS1. So when VDS is larger than VDS1, is basically the transistor is going to be in the saturation region basically, and that's under VGS1. On the other hand, for VGS2, we see that the drain to source voltage that causes saturation has increased. So VDS2 is larger than VDS1. Okay, so here what we conclude is, the third point is to conclude that saturation point, or essentially the VDS value that causes saturation, VDS set, increases in value as we increase the gate to source voltage, and that makes sense because VDS set is equal to the overdrive voltage, VGS minus VT. Right, as I mentioned, the drain to source current versus VDS looks as shown here, and it increases with VGS value. So this is the NMOS transistor, gate, drain, and source. This is a VDS. And this is the VGS. And essentially, here we sweep VDS for different VGS values. And let's say this is VGS1, VGS2, and VGS3, and we have of course VGS3 larger than VGS2, larger than VGS1. So obviously the drain to source current is proportional to the gate to source voltage. The higher the gate to source voltage, the higher the saturation current. So if we basically just focus on the saturation region, which when the current essentially is constant, we see that the saturation current, or the current of the transistor in the saturation region, increases with the gate to source voltage. The higher the gate to source voltage, the higher the saturation current. So as you can see, I set 3 is larger than I set 2, is larger than I set 1. And so we'll find that if we go through the physics, but again this course will mainly focus on circuit abstraction and circuit techniques. So we'll find that the drain to source current of the transistor in the saturation region is proportional to VGS minus VT squared. So essentially it's proportional to the overdrive voltage squared, because we said the overdrive voltage VOV is basically the VGS minus VT. So the drain to source current is proportional to the overdrive voltage squared. And again, the higher the gate to source voltage, what happens is we increase the number of electrons that are in the channel, so the channel conductance increases. And that's why we see that the saturation current increases as we increase the gate to source voltage. And also we'll find that the drain to source current, if we write down the equation from physics, but again this course is mainly about circuit abstraction, is given by 1/2 times a constant called Kn times V overdrive squared. So there is a constant of proportionality, which is 1/2 times Kn. Kn is called the NMOS transconductance parameter, and it's equal to Kn bar or dash times W/L. Kn bar is what's called the process transconductance parameter. So it's basically a parameter that depends on the manufacturing process that we are using to manufacture the NMOS transistor. So Kn bar is the process transconductance parameter for the N-channel MOSFET. W over L is called the transistor aspect ratio. What is that? W is basically the width of the channel. So essentially, if we have a 3D rendering of the transistor, this is the width of the conducting channel, this conducting channel here. And L is its length. So the wider the transistor, the wider the channel, the more current we can conduct. So say if this is the drain and this is the source, the more current that can flow from drain to source for the same gate to source voltage. The longer the channel of the transistor, obviously, we'll find that the conductance of the channel will decrease, and so the current that we can transfer through the transistor for longer channel transistor is going to be smaller, although we are using the same gate to source voltage and the same gate. Okay, and so this is the equation that governs the current in the transistor while it's operating in the saturation region. This region essentially while its current is constant. When VDS is high enough to cause the transistor current to be constant, we'll find that this current, as I mentioned, is going to be 1 over 2 times Kn, the NMOS transconductance parameter, times the overdrive voltage square, where the overdrive voltage is VGS minus VT. Now, if when we have VGS1, the transistor is going to enter the triode region at V overdrive 1, which is VGS1 minus VT. For VGS2, we see that this saturation point, which is basically the drain to source voltage value, that at which the transistor becoming the saturation region, is V overdrive 2, and then we have here V overdrive 3. If we look at this region, since this point, the current at this point, IDS, is governed by this relation, okay? So essentially, we'll find this boundary between the triode and the saturation region is given by this quadratic dashed line, which is basically half Kn V overdrive square. Okay. So I guess my point here is any voltage VDS higher than this quadratic line, the transistor is going to be in the saturation region, and for any VDS below this quadratic line, the transistor is in the triode region. So one more point here, we notice that the current of the transistor in the saturation region is constant versus the drain to source voltage. So for all these drain to source voltage values, the transistor current for VGS3 is of constant value. And here at VGS2, for all these VDS values, we find that the transistor current is constant. For VGS3, for all these values, the transistor current is constant as well. So what element provides a constant current despite changes in the voltage across its terminals is basically a current source. So if this is VDS and this is VGS and this is IDS, we find that the transistor in the saturation region can be modeled as a voltage controlled current source, and the reason is in the saturation region, if this is a gate terminal and this is VGS, this is the drain to source voltage VDS. So basically the transistor in the saturation region provides a constant current for different VDS values, and so we can model it as a voltage controlled current source where the value of the current source IDS is controlled by the gate to source voltage, or specifically the overdrive voltage, so half Kn V overdrive squared. Okay, so all here I want you to remember two things: the equations that govern the current in the transistor during the saturation region or in the saturation region. Number two, the transistor essentially behaves as a voltage controlled current source in the saturation region, since for different VDS values the transistor current is not changed. Unlike a resistor where as we increase the voltage across the resistor, the current in the resistor is going to increase. Now let's see the equivalent circuit and the model of the transistor in deep tried region. So I mentioned that if this is going to be the point of the saturation, so all points above that the transistor is in saturation, and below that it's in triode. And I like to mention that, or for the linear part of the triode region, the transistor is said to be in deep triode region. And as you can see, the transistor has a linear relation between its current and its voltage, and the element that basically behaves in this way is a resistor from Ohm's law. So the transistor in the triode or deep triode region specifically is essentially behaves as a resistor in deep triode. And this resistor, the value of this resistor is controlled by the gate to source voltage, specifically by the overdrive voltage, because as I mentioned, the overdrive voltage, which is VGS minus VT, the higher the gate to source voltage above the threshold, the more electrons that can accumulate in the channel, and so the conductivity of the channel enhances, and its equivalent on resistance is going to decrease. So this R on is controlled by the gate to source voltage, so the transistor in the deep triode region can be modeled as a voltage controlled resistor, where the value of its equivalent on resistance R on is given by 1 over Kn times V over overdrive. 1 over Kn times V over drive. And again, Kn is the NMOS transconductance parameter that we mentioned for the saturation region as well. So again, the equivalent on resistance of the transistor can be improved by increasing the gate to source voltage. Also, it can be increased because K over N is proportional or is equal to Kn bar times W over L. Equivalent on resistance can be improved by increasing the width of the transistor or width of the channel of the transistor, this part. And also it can be improved by reducing the length of the channel, L. So now we know the equation and the equivalent circuit that models the transistor in the saturation region. The current of the transistor is given by IDS equal to Kn divided by 2 times V over drive square. In deep triode region, the current of the transistor, as I mentioned, is essentially the transistor behaves as a resistor. In the saturation region, that transistor essentially behaves as a voltage-controlled current source. And in deep triode region, the equivalent on resistance of the transistor decreases as we increase the overdrive voltage. Okay. So if we have a transistor, or if we have the transistor in the deep triode region, this is the VDS. This is ground, and this is the VGS, and this is our own. So what will be the current in the transistor IDS and expression for the current? Well, IDS will equal to VDS divided by R1. We have VDS divided by R1 is given by this expression, which is 1 over Kn times V over drive. And so IDS is equal to Kn V over drive times VDS. Okay. Now, the remaining part that we need to model is this curve as the transistor current bends between deep triode and triode. So we'll find that the equation of the transistor in the triode region can be expressed as Kn times V over drive times VDS minus, to cause this curvature, minus VDS square divided by 2. Okay. And by the way, this model applies to the entire triode region, deep triode as well as triode. So all of this is the triode region, and its current is expressed by this equation. Why? Because when VDS values are very, very small, we are in deep triode region, we'll find that the quadratic term will have a very small value in respect to the first term here, and essentially the transistor model behaves, or the transistor essentially behaves as a resistor R on that has an equivalent on value equal to 1 over KnV over drive. Okay, so my point here is in the triode region you can express the current of the transistor by this equation. So let's summarize the current for the transistor, the equation or the model of the current in the transistor in different region. First of all, we have, so IDS has 3 parts or 3 equations. First, the current will be 0 in the transistor. If VGS is less than the threshold voltage, the current in the transistor is going to be 0 because essentially it's open circuit. Now, in the triode region, when VGS of course larger than the threshold voltage, then the transistor is going to be on, and we have one of 2 possibilities depending on the drain to source voltage. If the drain to source voltage is less than VGS minus VT, which is the overdrive voltage, we are in the triode region. On the other hand, if VDS is larger than the overdrive voltage, we are in the saturation region. So in the triode region, the current, as I mentioned, is given by Kn times V over drive times VDS minus VDS squared divided by 2. In the saturation region, the transistor current is given by Kn over 2 V over drive squared. And that's basically the equation that govern the current that's flowing in the transistor. And again, in the saturation region, the transistor behaves as a voltage-controlled current source. In deep triode region, the transistor behaves as a voltage-controlled resistor.